Welcome to this 13th lecture video for Physics 4A. In the last lecture set, we introduced the work and energy. In this lecture set, we are introducing impulse and momentum, which is what we need to start using momentum conservation in physics problem solving. We have about an hour-long lecture, broken into 3 parts, which will cover the definition of momentum, impulse, and how impulse relates to other quantities like momentum and force, and the conditions which govern the conservation of energy and momentum. And we have a couple simulation-based lectures in which we can apply and acclimate to the concepts we have been introducing in the last couple lectures and this lecture set. One of the lectures uses the algorithm simulation you have seen me use before. The second lecture uses the collision lab simulation from phet.colorado.edu, PHET.colorado.edu. Please note that we haven't started solving physics problems using conservation laws yet. We will devote most of the next lecture set to working out examples of problems which can be solved by applying conservation of energy and/or momentum.
With this momentum that we are going to talk about, it relates to a question I asked early last week. I was using this as a conservation of energy demo, and in some sense you saw that when can everyone see this okay? Yes. In some sense you saw that when I lift a ball to one side and let go, then only one ball comes out the other end, and it reaches the about same height that this started out from. So when I let go here, this whole thing is starting out with some amount of energy, and that amount of energy is conserved through this interaction. Now, I asked a question last time that you didn't really have tools to answer. So if all we care about is conservation of energy, then why doesn't this happen? Why doesn't it happen so that when I pull these 2 balls to the side and let go, why doesn't it happen so that after they hit, only one ball comes out with the energy of both balls? Like that would conserve energy. But that doesn't happen. And what we sort of say in physics is that when you see something that could have happened but doesn't happen, that means there must be some law that's forbidding it. So there must be some other thing that has to be conserved so that when this comes and hits, that one ball coming out with some appropriate amount of speed so that it reaches this height, that doesn't happen. Because this interaction here is obeying some other conservation law beyond conservation of energy. This is something that happens because this has to obey all the conservation laws. And that's what we are going to start talking about today. So let me do this in a slightly different order than what I usually do. And I'll start by defining momentum. Let me just start out with that. And so, when we did energy, I sort of eventually came out and told you guys that I can't define energy. There's no way to define it. But with the second quantity that I'm going to tell you that is conserved, let me just define what momentum is so that we have something to talk about. And we'll justify soon why we define the momentum the way we actually define the momentum. So momentum is a new quantity that we are defining. So let me start out with a symbol that we use for momentum. For some inexplicable reason, the symbol we use for momentum is P. That's just the symbol that everyone uses. Lowercase p, not uppercase. So momentum, lowercase p, is defined as mass times velocity. Or let me keep so if I write it out as a momentum, then that's equal to mass times velocity. Or we don't make a habit of writing things out like that. So in symbols, it'll be momentum P is equal to mass times velocity. I want to touch on something that I should touch on now. What kind of quantities are mass and velocity? As in, whenever I ask that question, it's a question of is it a vector or scalar? If it's a vector, then I care about the direction. If it's a scalar, then I don't care about direction. So mass and velocity. Is mass, what kind of quantity is it? It's a scalar. Mass doesn't have a direction. What kind of quantity is velocity? It's a vector. Velocity has a direction. So what you see on the right-hand side here is that this is a scalar multiplication. You are taking a vector and multiplying it by a scalar. And if you recall back to the vector algebra that we were covering last time, that means momentum should also be a vector. So when something has a momentum, then that sense of the momentum always comes with the direction. So as an example, this cart, it can have a momentum. So when I push it from left to right, it'll gain a rightward momentum, and then bounces and then comes back. So right now it has rightward momentum, and when it comes back, does it have the same momentum when it's coming back? Same in magnitude. So you have the sense that however much movement this has, it's the same amount of movement this has. But so with the kinetic energy, we didn't care. Energy was a scalar. But this is the one distinction I want to draw from the start. This is going to be a vector. So we are going to care, is it moving to right or left? So when this cart is moving to right, it has rightward momentum. When it's coming back, it has leftward momentum. Yeah? Let me try to make a sense of this definition in two ways. So one is, so when we say this cart has rightward momentum, does that description match with the English definition that Jared was giving? That momentum means like something is moving and it'll keep on moving unless something stops it. Is that what you said, kinda? Yeah, okay. So does that, how we define the momentum here, does that match with that intuition? Okay, that's mass right now. When it has zero velocity, that's zero momentum. So let me give it a little bit of push so that it has non-zero velocity. So it has rightward momentum. So I guess, so if there wasn't this rail here and this track went forever, would you expect this to move to the right forever? According to laws of physics, yeah. If we can ignore friction, you would expect it to move forever, right? So that's one sense in which the way we are using the word momentum in physics matches with the natural intuition you have for that English word. I mean, that's why we picked it. Here's the second question. So this cart weighs about 500 grams, or its mass is about 500 grams. I can add another 500 grams to it, have it double the mass. So I guess this is the question. When this cart has double the mass, then according to this formula, if I gave it the same velocity as last time, then it should have double the momentum. Like, what do you think that means? That when I give it the same velocity as last time, somehow it has double the momentum that it had when it was moving with that 500 gram. Like, what does that mean intuitively? Okay, so it does relate. So I've just said that force that momentum exerts will be double. Now I do want to say force does relate closely to momentum. We are going to look at that either sometime today or very soon, sometime this semester. So it does relate to force. And in fact, let's look at it this way. I can actually try to measure how much force it takes to try to stop this cart. I'm gonna use this wick spring to kind of pull on it and bring it to a stop, right? So that's how much sort of force it takes to bring it to a stop. And when I make it heavier and give it the same velocity as it had last time, then you are going to see, yeah, it does take more amount of force to bring it to a stop. So, so that's why this mass is here. So, so this is the definition of momentum. And now I want to spend about 10 minutes or so justifying why we define it this way and how this is a conserved quantity. That in many interactions you will see that this quantity will be conserved. And I want to draw a distinction from how we cover the energy. With the energy, I didn't give one definition of energy. I simply said we want to define energy however we can so that it's a conserved quantity. That's how we arrived at all of this. I didn't define kinetic energy. I just wanted to make sure as I did the work, the energy of the whole thing was conserved. So that's how I arrived at this. With the momentum, we actually go the other way. We are going to, this is our definition of momentum. And you will see that from the laws of physics that you already know, that this has to be a quantity that's conserved under a very specific but general set of circumstances. So let me give you an example of momentum conservation. So I have these two cards. Let's see. Let me make them collide this way. So what I'm showing right now is what's going to be called the elastic collision later today. So right now, they both have zero momentum, right? And if I make this card move at some speed, then it has some amount of momentum, right? And if I make this card move at some speed, it has some amount of momentum, right? Now watch this. I'm going to push this card to collide with this card which has zero velocity. Yeah, zero velocity. All right, would you say momentum is conserved in this collision? Yeah. So this comes in with some amount of momentum. It hits it, and then it continues. So this card's momentum has changed because after the collision, this stops, but the other card is moving. So when you look at the entire system of the cards, then the total momentum of the two cards is conserved. So you can see that here. The other two examples, it's a little bit harder to see. So when you look at this collision right now, they are going to stick together this time. So when they stick together, would you say that the momentum is conserved? Yeah. So it may be a little bit harder to see. Before you saw that speed didn't change, right? Here, when they collide, speed does change. How much would you say speed changed by? Like a factor of 2, right? So if the speed decreases by a factor of 2, but mass increased by a factor of 2, then the momentum would still be conserved. Let me give you one last example before we actually go into equations that tell you exactly how this happens. Okay, so this time these two cards are going to collide, but one of them will be 3 times as heavy as the other one. Any guesses how they would, after they interact, how they would move? So let me call this A, call this B. So I imagine B would bounce back, right? That doesn't. How do you think A would move? 1/3 what?
1/3 of its speed.
1/3 of its initial speed? I'm not sure. Oh, wait. In which direction? Moving to the right or left?
Left.
To the left? Okay, let's look at this. After they collide, so this starts coming into the right. How many people think this will continue moving on to the right? How many will think it will bounce back to the left? All right, let's see. So I'm going to let it come in with some speed. It continues moving to the right. So now this interaction gets complicated enough that if I asked you, is momentum conserved? I don't know. Unless I measure all the speeds very carefully, it's going to be hard to see. Let me do, one last example. So this is the one that what Arjun was saying could happen. So when this cart B is heavier, when they collide, A actually bounces back. So to be able to drive motion of this cart, like in this case, that's why we are introducing these quantities that we are introducing. So let me introduce it now. So this is something that we call impulse. Definition of something that we call impulse. It's just a word you have to know. I don't know if I try to give some intuitive meaning for this impulse. It's just going to be something we define. Let me just write it down. I think your textbook uses the letter J. I never got used to it. So I'll just say spell out impulse. I'm not going to try to use a letter. But I think your textbook uses the letter J. But whatever. Impulse is defined as this. It's a force times duration of time. You have seen a similar definition before. So I want you to compare this definition of impulse to the work that we defined before. So we defined the work this way. Work was defined as force times displacement. So impulse is different in an obvious way that, here I had position, change in position. Here, now I have change in time. So that's a rather obvious difference. There's one other subtle difference about impulse as compared to work. Any guesses? It's a vector quantity, yeah. So with work, it was a product of two vectors, and we defined the product in such a way that it gave us a scalar. This is the dot product. Time, does time have direction? No, you could have positive and negative interval, but that's just, but time doesn't have direction. If you can say something is upward or downward or left or rightward, it doesn't have direction. So time doesn't have direction, meaning this is a scalar. So vector times scalar, that's just going to give you a vector 10 out of 10. So impulse is a vector. It's a vector quantity. So this is the quantity that we are going to define. And here's the thing that's useful to know about impulse. It's, once again, I want to keep comparing it to work because the role of, this is like the SAT type analogy. Impulse is to momentum the same way work is to energy. So let me finish this out. Impulse, this is how we define impulse, but this how we define impulse, we will see soon that it happens to give us change of momentum. And we'll go through the quick algebra to show that impulse gives change in momentum of an object. And just to complete this comparison here, work, as I keep bringing up every single day I mention it, work is important to us because it gives us change of energy. If you're interested in how momentum of an object might be changing, then we would look to impulse. Well, how much impulse was on that object? Let me give you an example here. So I have a golf ball. And when I drop the golf ball, this golf ball is going to have some amount of momentum just moments before it hits the table, right? So I drop it, and the moment before it hits the table, it's going to be moving at some velocity downward, so it's going to have some downward momentum. Does the momentum of this golf ball change as it strikes the table? Right? So moment before hitting the table, it was moving downward. Moment after hitting the table, it's moving upward. So the momentum of this golf ball is changing as it's undergoing collision with the table. Like if you could do a high-speed camera, you would see the ball kind of strike the table, and there's some deformation, and you would see it bounce back. Right? So I could, in this example, I can ask this question with a golf ball example where I have a ball that's moving downward at some velocity before it strikes the table, and after it strikes the table, it let me call it V before, and after it strikes the table, it moves up with some velocity I'm going to call V after. I could ask, what is the change of momentum of the ball. And that change of momentum, if you look at what I have written in this line, then it's going to relate to the impulse. Now, looking at the situation here, would it be easy for you to calculate impulse using the information given here? Like if I asked you to do that, find the force on the ball, find the duration of collision, and then find the change of momentum of the ball. Would you be able to do that? What do you think the force between the table and the ball was during the collision? You don't have any piece of information there, right? And what about the duration of time? What do you think the duration of time was for the collision? I guess it's less than a second. How much less than a second? 0.3? 0.3 seconds is actually surprisingly long. 0.3 seconds is a third of the time it takes for me to say 1,001. It's like saying 1,000 in 0.3 seconds. Do you think in the time where it's colliding, I have time to say 1,000? Could be less than 0.1 even. Because it's however long of a time it is for you to produce that thunk sound. So here's the situation where if you're trying to calculate change in momentum this way, I don't know how I'm going to calculate it. I probably did this in wrong order. But that's not to say that this is useless, because there are situations where this is useful. Like if I want to figure out how much momentum of this cart has changed, then somebody could be applying a force in a way that you can actually measure the force, and they can be applying it for a fixed amount of time, so that after the fixed amount of time, you can actually calculate how much impulse there was, and use that to calculate the change in momentum. So what I want to get you to used to is how to calculate this change of momentum in two different ways. One would be through this impulse, which sometimes you can, sometimes you can't. In this situation, what would be easier way of calculating the change of momentum of the ball? Not a trick question. It's got a really simple answer. Like, if I just told you the definition of momentum, and I asked you, okay, ball is bouncing like this. What is the change in momentum of the ball? What would you tell me? Steven? Yeah, that's how you define any kind of difference, right? So you could say this is, momentum after minus momentum before. Well, I see this here, so I just plug in whatever numbers I have. So say this is mass can factored out. Mass times velocity after minus velocity before. And if you have really good physical intuition, you might go this far. You might have some sense that the speed of the ball is same before and after, right? So if you have that, you might go this far. So, if I call the magnitude of this V naught, then, magnitude of this would be also V naught. And you would say, so it's plus V naught minus V naught. So the total magnitude of change of momentum will be 2m V naught and upward for the vector quantity. Right? Yes? Good? So yeah, this is another way you can calculate change of momentum. And this is actually why it's useful for you to know this definition of impulse. Suppose I asked you if that this collision takes 0.05 seconds. And now I ask you how much force is on the ball during the collision. Do you have enough information to answer that? Yeah, you should tie this change of momentum that we calculated using definition of momentum rather than this impulse thing, but you can tie it back to how impulse is defined. Say that this is equal to impulse as defined here, which means as soon as you know the duration of the interaction, then you can figure out, well, I guess I should call this average force. This is the average force during the collision. Okay. So these are the two new important quantities that we are defining new today. And I will describe now how this definition of impulse and momentum tells you that total momentum is conserved in many cases. Okay. So let's first, let me show you this portion. That impulse defined this way does really actually describe change of momentum. Because I just gave this to you without justifying it. Let me justify that. So let's put it this way. I have some object here of mass m. And let's say somebody says that I'm applying some force for duration delta t. And the question would be, all right, what is change of momentum due to the force? Right? So I can approach this in just a standard, straightforward way. I want change of momentum. That means I want change of this quantity. So I'm looking for what is the final momentum minus the initial momentum before I started pushing it. This could easily be 0, but I just want to keep it general. All right. So this would be equal to, using the definition that's written there, I'm just going to write it out. Mass times V final minus mass times V initial. Factor out mass. So mass times V final minus V initial. Seems like I'm stuck for right now, because the information I'm given has nothing to do with the velocity. The information I'm given has something to do with applied force and the duration of application of force. So, thinking back to what you know about forces and what you know about kinematics, how would you connect from here to this information that's given? Yes?
Change in velocity, acceleration?
Yeah, so you can relate change in velocity with acceleration. Let me write down the formula that you should remember. So acceleration is defined as rate of change of velocity, or I could write this out as final velocity minus initial velocity over duration of time. All right, that's gonna be useful somehow here. So let me actually plug this in here. So then it's going to be, so mass is still the same mass times. So imagine solving this for this, then it's acceleration times delta t. So acceleration of the block times delta t, the duration of its acceleration. Yeah. Staring at this for a while, I realized that I can regroup this. I can group this way instead. Right? Okay. So then, okay, mass times acceleration. Well, here the only force that's being applied is the applied force. There's no other horizontal force in effect. So this force is mass times acceleration. So I can say this is equal to applied force times the duration of application of that force. And, well, that's equal to impulse, the way we defined it. So that's why this change of momentum is equal to impulse. Yep. Questions? Comments? I guess this is actually a good time for me to introduce this idea. Yeah, I don't know. Different semesters I do it at different times, but I think the earlier I can do it, the better it is. So let me do it now. When you look at this expression for too long, or maybe about the right length of time, you might, I hope you wonder whether this is true. If you can write out force this way, if you can say, apply the force, can be measured instead of saying force is mass times acceleration. If you could say force is, well, impulse or change of momentum. To apply the force is change of momentum divided by time. Does this sound plausible? Yeah? That applied force can be expressed this way instead of the way we are used to saying it, that force is equal to mass times acceleration. Like, this sounds plausible, right? And in fact, if you are following this chain of equalities, you might say, all right, so that's two different ways of expressing the same idea about force. And what I want to tell you is that, so far you haven't had a situation where you would have to pick and choose between these two. They are both true, they agree with each other. That's what you see here. And what I would tell you is that there will be situations in the future where they actually disagree with each other. The most common example that's cited, so I'll give that example to you. The most common example that can be given is this one. So it's a space, I guess, aerospace application rocket. So imagine you have a rocket in space or somewhere mid-flight, and everyone here knows how a rocket works? Does everyone here know how a rocket works in vacuum of space, where it doesn't have anything to push you against? There's a very amusing New York Times editorial back in the 1920s saying how the rocket couldn't work in the vacuum, but it turns out, as you see in Apollo programs in the 60s, that rockets do work in space. So they published a retraction in 1969. You guys never heard of this? Never mind. But rockets do work in the vacuum of space. So if this is, in terms of how you get yourself to move, the way you normally move is you move by reaction force. As in, when I walk, when I walk, so the way I walk is using my foot, I apply a force to the ground, I push the ground back. And because of friction, because I'm wearing good shoes, ground pushes me forward. That's how I move forward when I walk. Or if you're swimming and you're not a good swimmer, then one way you can move fast is you just push against the wall. You apply normal force to the wall pushes you back, so you move forward. So the rocket propulsion, it's going to be the similar idea. The rocket pushes something backward, and that something pushes the rocket forward. What do you think that something that's getting pushed backward is?
Fire. Fire.
Sorry, what? Did you say fire? So there's a combustion going on in here, but fire is an idea, not an object. You have to push an object backward. Ratana? Huh?
Some of the part. Something. Some of the part of the rocket.
Something that's a part of the rocket, yeah. So in the rocket propulsion, so rocket actually carries its own fuel. In the vacuum of space, there's no oxygen to cause combustion with, so rocket has to carry oxygen and everything with it. And so there's combustion here, and the pressure pushes out the particles that it was carrying as part of its fuel. So the way this rocket is propelling itself is essentially, imagine some part of the rocket, the fuel, that's getting pushed outward. And as a result of the push, the rocket is getting, so let me call this the action force. And as a result of push, the rocket gets the reaction force from its fuel, and that's how it's moving up. So looking at this situation, somebody could ask you, what is the force on the rocket? And if you naively calculate force this way, as in, let's say you are given the trajectory of the rocket, so you know its position as a function of time, which means you know its velocity and acceleration as a function of time, right? And somebody asks you, what is the force on rocket? And if you answer this question with saying, with the answer that force is equal to mass times acceleration, you'll be wrong. Force on rocket in this case actually will not be equal to mass times acceleration. In fact, so we have two different expressions for force, right? So far, this and this. And this is the situation where these two expressions will disagree with each other. So you have a choice of, what is going to be the force on this rocket? So you could say, well, maybe it's the formula that I already know. Maybe it's mass times acceleration. Or maybe it's given by this new expression, change of the momentum of the rocket divided by change of time. Like why? So we saw before here that these two expressions agreed with each other. So in this special situation, why would these two expressions now not agree with each other? Like why wouldn't it be that they are both correct or they are both wrong, if that could happen? Like which part of the description of the rocket here makes you reconsider some of the steps that are being done here? Stephen?
Mass not being a constant.
Yeah. Here, because of the way rocket propulsion happens, mass of the rocket is a function of time. Which means, when you look at the derivation here, I kind of implicitly assumed that the mass is constant. And that's true most of the cases. But if that's not the case, as in I have to say final mass and initial mass, then this step here doesn't work. And I need this step to relate this directly to acceleration. So once you say this, then the rest of the steps become questionable. Like, is that no longer, you can't do this factorization anymore, which means you can't do this anymore. And now can you say this? And let me just tell you this as a matter of you knowing something about physics. This is something that somebody just has to tell you, that the first expression, which is the expression that you are familiar with, that's wrong. Turns out force is not equal to mass times acceleration. So this is one of the few lies that I will admit to telling you in this class. So we do start our introduction to force with the mass times acceleration, but now I am telling you that that's not really how you want to define a force, because it's not going to be true all the time. It's true most of the time, that's why you started out with it, but this is the case study that tells you that this is wrong. What is correct is the second expression that we are telling you now, that force is equal to rate of change of momentum. And in fact, this is actually the definition of force. So I will take this to be the actual definition of force, that force is defined to be rate of change of momentum. So, why wouldn't I start out with that to start the semester? Why do I drag you through all that path, with all this? Like, why didn't I start out by just telling you on the, not first day, but the first day of the third week, that force is rate of change of momentum? Why didn't I do that?
Don't help us with that.
Yeah, we haven't introduced the momentum yet. So I could have told you this from the beginning, but you wouldn't have understood because, well, I had to define momentum. But unless you went through some of the dynamics using this as a crutch, then we wouldn't have concept to even describe this. This is one of the senses in which physics is cumulative. That this is one of the fundamental definitions of that you need to know as you're doing physics in the future. But for you to understand this, you kind of had to be bootstrapped into knowing something about mass and velocity and sort of seeing the sense for this. So here, what I would say is that we actually bypass all of this. So the actual correct expression here is that this is equal to the applied force times change of time. So, this will be true whenever mass is constant. Whenever mass is not constant, we don't worry about this at all. We just go to this directly. Good. And this expression here, oops, not this one. This expression here is the one that's actually correct all the time. The second expression, it's often correct, but not always. Yeah. All right, so I still haven't told you why momentum is conserved, right? So to explain why momentum should be conserved, let me use this example that you guys saw at the beginning of the class today. So when you see these two carts interacting, here's one scenario where momentum was clearly conserved. After they collide, momentum of this cart was somehow transferred to this cart, and that's it. Momentum is conserved. So let me use that as an example to try to derive why momentum should be conserved. So we are looking at this situation here. I have a frictionless surface, and mass 1 is moving to the right, and mass 2 is not moving initially. And I guess I don't really care if they are moving or not. So here's another way the momentum can be conserved. If they're both moving towards each other, after collision, they kind of move away from each other. So here, what would you say the total momentum is before the collision? What is the total momentum of the carts A and B? So what kind of momentum does cart A have? So are you saying the total momentum is 0? Yeah, total momentum should be 0. So cart A has rightward momentum, cart B has leftward momentum, so they balance each other out. You add up, you get 0. So before collision, they had 0 net momentum, and after collision, they also have net 0 momentum. So in this interaction, the one where you could clearly see that momentum was conserved is this one. But I'm saying, how they are moving, I don't really care. So how these two are moving, I don't really care. What really matters to me is the interaction between them. How cart A is pushing cart B. So since I'm using labels A and B, how cart A is pushing cart B. That's the description that I care about. So let me draw a free body diagram to try to see how I can go from that description of the interaction between these two masses to the result that momentum should be conserved. So these are the free body diagrams of these two masses, mass A and mass B. Let me ignore all the uninteresting forces like gravity and normal force. Gravity pulls it down, normal force balances it. Nothing really interesting happens with those. So let me just draw interesting forces here. When you look at the interaction between cart A and B, is there any force on cart B? I mean, looking at cart B, would you conclude that there is a force on it? Right? Yeah, it's the magnetic force which we are trying to not to talk about. But there's a force on cart B. The way you know that is, well, it's getting pushed to the right. It's accelerating to the right. So you know that there must be some kind of force on cart B. Let me just label that as force on B. All right. Is that it, or should I have additional forces on my set of free body diagrams? What? Okay. So what do you point to and say, this is why there's a force on cart A?
So it has an initial velocity and then it goes to 0.
Okay. So you see cart A accelerating also. It had a rightward velocity. When it goes to 0, that means it's accelerating to the right, to the left. So the cart A also accelerates similarly to how cart B accelerated. So there's a force on A that's to the left. Force on A. All right. I guess since I know there are masses, if I have force on A and force on B, then I guess that's enough to calculate the change in momentum. I do have to kind of assume some amount of duration of time. So, some duration of interaction. It might take, half a second or whatever. So let's try to calculate the net impulse. So the net impulse on both of these objects, and from what we were saying about impulse, why did I erase it? From what we were saying about impulse, that it's the change of momentum. If we calculate net impulse, that should tell us what the change of net momentum is. Okay? So what net impulse should be is impulse on block A plus impulse on block B. So that would be the force on A. That's the only, it should be net force on A, but that's the only force on A. So force on A times some duration of time plus force on B times some duration of time, right? Yeah?
What kind of force is it?
Okay, so here it's magnetic force, right? They are not touching each other. But it could have been normal force. So I don't want you to get too hung up on the nature of the forces, because it could have been something like this. I have these two balls, and here. All right. So it could have been these two balls interacting with each other. So in this case, the force is normal force, but the result is similar. So, like this. So I don't want you to get too hung up on what kind of force it is. What's important here is that, well, there's some kind of applied force on B, and there is some kind of applied force on A. But maybe we should talk about how these two are related. Are they related? How are they related, Ali?
The force on A is from B.
Okay, so force on A by B. Okay, what are you trying to say here? And vice versa, force on B by A. So you're still trying to tell us something that you haven't quite come out and said it.
I'm also thinking when you apply force on A, shouldn't there is a force on A as well?
I see. So since this is force on B by A, you are saying there should be reaction force on plug A.
And when you apply force on A,
By B, that there should be reaction force here. Hey, aren't these the action-reaction force pairs? Yeah, these two forces that we have already drawn, they are the action-reaction force pairs. So these are the action-reaction force pairs. And as I keep saying, whether you label one the action and the other the reaction, or if you swap them around, say this is action and that's reaction, in terms of Newton's third law, it doesn't matter, because they happen simultaneously. As in, this is what I mean. So if for these two carts, if this cart B wasn't here for A to apply force on, then A would just go on without experiencing any force there. The only reason A is experiencing a force is because cart B is here. So because of the presence of cart B, the A, as it's trying to push through here or move through here, it feels a force that pushes that way. So in that sense, you could say, well, this is the action force. A gets pushed back, and this is the reaction force. But what matters here is that these two forces are related to each other by Newton's third law. So what does that tell you about this quantity here that I was writing? Yes?
The force on A should be equivalent to force on B.
Yeah, so I could actually rewrite it this way. So this is minus force on B, right? Equal in magnitude, opposite in direction, times delta T plus force on B times delta T. Hey, that looks like that adds up to 0. Yeah. We should probably touch on this. I wrote down from the beginning same duration of time instead of saying delta T A and B. Was I justified in saying that the duration of the time is same is for both forces? Yeah, because these two are part of the one and the same interaction. The moment this force goes away, this force also goes away. So these two times should be the same time, which means everything is justified. And net impulse is equal to 0. This is the net impulse. Net impulse is equal to 0. So now, does it matter if these two had the same mass or if one was heavier than the other? Does that affect whether the fact that net impulse here is 0? It doesn't, right? So actually the way I started out saying that they had a different mass. So whatever mass that these have won't change the fact that net impulse has to be 0. And really, this is what I want you to impress on you, that what we wrote down here, this was the important step here. This is coming from Newton's third law. I think when we covered Newton's law, did I tell you Newton's third law is the most important of the 3 laws of Newton? I didn't. I might have said it's the most confusing one, but it's also it's the most important one. It's because of Newton's third law that we can say this, that we can say net impulse here is 0, and because of this, through this, we can say that it's from Newton's third law that we can say this, that momentum is conserved. As in, if net impulse is equal to 0, then, net impulse is what gives change of the total momentum. If net impulse is equal to 0, change in total momentum is 0. If momentum is not changing, that's what it means for it to be conserved, that it's not changing. So I said at the beginning of today's class that with the momentum, we are not going to start out saying that it's a conserved quantity, that we are going to derive that it should be a conserved quantity. This derivation here, it follows directly from Newton's third law. In fact, you could say these two things are equivalent to each other. Momentum being conserved means Newton's third law is correct, and Newton's third law being correct means momentum is conserved. If you guys take other like upper division physics classes, like electrodynamics, this will come up at some point. Because there are situations you can think of in electricity and magnetism where it appears as though Newton's third law is not correct. There, I want you to have this intuition that Newton's third law has to be correct. Otherwise, this one of the most important law of nature, the moment you compromise this, you compromise this. Because they are one and the same thing. Newton's third law, so I call it law of interaction. I can also call it law of conservation of momentum. So So with the energy, there wasn't any law that said energy must be conserved. We kind of constructed energy in such a way that it must be conserved quantity. With the momentum, we start out with this definition of momentum, and here's the law of nature that says this must be a conserved quantity. But let me clarify this a little bit, because when you look at any given system, it's clearly not true that momentum is always conserved, because, let me test this again. Okay, it's clearly not true that momentum is always conserved, because right now, look at it, momentum is 0, right? And now momentum is not 0. And in fact, momentum seems to be changing regularly. So when we are trying to describe a system, I want to come up with a statement of condition where I can say if this condition holds, then momentum is conserved. If this condition doesn't hold, then momentum doesn't hold. Momentum conservation doesn't hold. Do you guys remember what we did with the energy? So, we said, we might not have done this explicitly. So with the energy, we started out saying the total energy is always conserved. But in this class, we don't really look at the total energy. We look at mechanical energy. So what we are able to look at in this class is what we call mechanical energy. That is kinetic energy plus potential energy. And we may not have said this. When would you say that mechanical energy is conserved? So mechanical energy is conserved when ... I want to come up with some concise statement that I can use to say whenever this concise statement is true, I can say mechanical energy is conserved. Whenever this concise statement is not true, I don't know if mechanical energy is conserved. So let's just start out with that. So let me give you an example. So this cart moving back and forth, does this conserve mechanical energy? Sort of ignoring friction. Is the mechanical energy conserved as this bounces back and forth? Right? Yeah, it's moving at some speed. It has some kinetic energy. And once again, ignoring friction, its speed should not be decreasing. So we would say, yes, mechanical energy is conserved. So, friction not being there is an important part. But I want to be more general than that. I want to be more general than saying mechanical energy is conserved when there's no friction, which is actually true a lot of the time. But I want to actually have a statement that's bulletproof. There's no situation where the statement is not true. So, in other words, what leads to the change of mechanical energy? If you ever saw mechanical energy changing, what do you blame that on?
The non-conservative forces.
You blame that on non-conservative forces. Meaning, here's an interaction involving conservative force. When I take this ball and drop it, before it hits the table, its kinetic energy has changed. But because gravity is a conservative force, there's a potential energy we associate with it. So we can say whatever change in kinetic energy, it came from change in the potential energy. Right? Now, the moment it hits the table, you see mechanical energy actually changing over time. So which force would you point to and say that force is changing my energy, mechanical energy? What non-conservative force do you see here that's changing the mechanical energy of this ball? Yeah, normal force. So normal force is not a conservative force. Now, a lot of the situations where you see normal force, it might actually end up, so you could have normal force present and have mechanical energy still be conserved. So I don't want to say, so this is one example of statement that I don't want to say. I don't want to say mechanical energy is conserved when there is no non-conservative force. I mean, that statement is true, right? If there's no non-conservative force, like when this ball is just dropping in free fall, then its energy would be conserved. But the reason I don't want to say that is when you look at this cart sliding back and forth, is there a non-conservative force acting on this cart? What's the non-conservative force acting on the cart? Ignoring friction. Normal force. Normal force is acting on this cart. So why is the normal force not changing the energy of the cart? Now, it happens to be balanced out, but yeah, that statement is probably true, but I want to look at something that relates only to the normal force. I don't want to bring in any other forces. So why does normal force not do any? So here's another way to put it. So the reason normal, Stephen, you're going to say something?
Because it's perpendicular to the motion, so
Yeah.
it wouldn't affect it at all.
Yeah, so normal force is vertical. The displacement here is horizontal. So when you calculate the work done by normal force, that's going to be 0. So normal force, even though that's there, it does no work, which means there's no change of energy due to normal force. It's a different situation. If from here, if I lifted this up, then normal force would actually do work and change the energy of this cart. So that's really the concise statement we want to say. We want to say mechanical energy is conserved when, so this is the statement I want to be very careful in stating. So I'm looking at the net work, the total work. When the net work by non-conservative forces it's going to be longer than I thought. Non-conservative forces is equal to 0. Okay? So this is the condition. I hope this makes sense to everyone from what we've been talking about last week, that even though I kind of forgot to mention this in class, that this makes sense. That work is what gives you change in energy. So we want to say that whenever this condition holds, then we can say mechanical energy is conserved. So conservative forces doing work, you don't worry about that because you can account for it in the potential energy. You would maybe worry about non-conservative forces, but only when they are actually doing work. Because when they are not doing work, then even non-conservative forces will not be changing energy. Yeah? So thinking about this, I want to now come up with a statement for when the momentum is conserved. Because here you clearly saw the situation where momentum is 0 right now. It's not 0 now. And in fact, it seems to be changing back and forth. The momentum seems to be changing direction as this cart moves. So I want to come up with a statement that would say, all right, whenever we avoid this, we can say momentum is conserved. Let me ask you this question. What kind of forces would you blame for momentum possibly changing? Momentum of a system possibly changing. So as a reminder, with the energy, the kind of forces that we blamed this on was the non-conservative force. That's the forces that had the possibility of changing energy, right? With the momentum, we actually don't care if a force is conservative or not. Like when you look at this, the kind of collision between these, that force involves non-conservative force. You can tell because it makes a loud sound. And this doesn't conserve energy. But in this interaction, you will find that momentum is actually conserved. So with the momentum conservation, we are not looking at is the force conservative force or not. We are looking at a different label for the forces that either we worry about or we don't worry about. I don't have too much time, so I might have to speed this along. So let me walk you through here. So this is our derivation saying that net impulse is 0, therefore momentum is conserved, right? So what we are doing right now is trying to think of a way how this could go wrong. For each of these steps, how that step maybe is not always true. So, I mean, net impulse is change of impulse of these two objects. That seems like that should always be true, right? I wouldn't worry about impulse of some other object. This is how impulse is defined. So there's no situation where this wouldn't be true. And on the next step is where we had that fortunate coincidence, where one force was able to be paired up with another force, and we could say they cancel out, therefore equal to 0. What would you need to see happening in this system so that I don't have this fortunate coincidence anymore? What are the situations where you could not look at a force in your free body diagram and say, there's my reaction force? We actually had a description for that. Aisha? Yeah, external forces. So, we didn't say it out loud when we were going through this, but one thing that's special about these forces here is that they are internal forces. They are force from, this is a force from another object within your system. So when you look at this impulse, you could say, oh, there's another impulse that pairs up and balances out to 0. But if you ever have an external force, you wouldn't be able to say that. That's exactly the situation you have here. When you are looking at this card, I am external to that system. So when I apply a force on the card, there is force on my hand. But so if you look at the net momentum of the cart and me, but then I'm standing on the floor, so I guess you'd have to include the earth. So if you include the if you talk about net momentum of the entire earth, then it's going to be conserved. But it's going to be hard for you to see that. So here, so that's why we don't go to that end. We say whenever there's an external force, then the net momentum might change. Right? So when I apply external force, then momentum of this is changing, and that's what you see here too. The track is external to the cart. So whenever this interacts with the track, that's when its momentum is changing. Good. So for today, let me start us off here. Let me start us off here saying momentum is conserved. For now, I will say this. When net external force is equal to 0. I want to actually refine this because this is not exactly correct. There's a small refinement I need to make to this. But for today, let me leave it there. And I'll come back to refining this statement later, probably on Thursday, as we look at more conservation law problems. Yep.
So let me bring this back and show you the second half of that demo. This is one of those things that might be helpful in problem solving because it relates to some of the things that people sometimes forget about, or sometimes it's coded, the information is encoded in the question wording ever so subtly that unless you are reading it very carefully, that people sometimes miss. So let me ask you two different questions that sound very similar, but are actually setting up the situation differently, and the answers end up being different. So I'm just gonna set the material property so that this is back to its original mass of 1 kilogram. And I don't remember, thruster property was T, okay. Okay, so someone could ask time speed, okay. Someone could ask this question or set this up. So you are pushing two different masses, two different blocks of different mass between two posts or over some distance. And the question says you push them into equal force over the distance. And the question asks you at the end of that push, which block has greater momentum or greater energy. So the last time I did this demo, I was imagining someone would ask you which block has greater kinetic energy. And let me just redo the plot so that I have something there. So this would be one with the lighter mass. So try to stop it around here when the front reaches there. And let me go back, and I'm going to make the mass now heavier and do the same experiment. Just mute my phone. Let me restart this. Find this correct. And the question might ask, which of the two blocks have greater kinetic energy, or do they have the same kinetic energy? And the answer is they have the same kinetic energy. Now, suppose someone asks you, which of the two blocks have greater momentum? Then you might be able to quickly calculate from the things you know about momentum, P is equal to mv, that this heavier block, that's heavier by a factor of 2, should have greater momentum since its speed is it's greater than half of this. So you might be able to figure it out that way. Now let me change the wording of the question slightly. So in the previous question, the hypothetical imaginary question, I had it set up so that the two different blocks are being pushed between these two endpoints over the same distance, pushing with the same amount of force by using this thruster. Now I'm going to change the question wording ever so slightly, so that instead of the two blocks being pushed over the same distance, instead this time the question is, the two blocks are being pushed for the same amount of time. And let me do a simulation of that here for the second heavier block being pushed for the same amount of time as the lighter block. And let's see what happens. Same amount of time. There it is. Now, when you see it in the simulation, I think it's easier for you to see why you get a different answer. Because now, if someone asks you which of the two blocks have greater kinetic energy, then it's the lighter block that has the greater kinetic energy. And if someone asks you which of the two blocks have the greater momentum, then this time the answer is they have the same momentum. And it comes down to a very subtle difference when you are looking at so this was the quantity that we are looking at in chapters 7, 8, and 9. When you are looking at change in the energy or change in the kinetic energy, the physical quantity that most directly relates to change of energy is amount of work being done. And the definition of work is force, the vector, the product with the displacement. And now that we have covered the momentum, we can talk about the change of momentum. So if you are looking at change of momentum, which I think your textbook uses the letter J for impulse, sorry, I'm never gonna get used to this. I'm just gonna spell out impulse. Change of momentum is related to impulse, which is defined as force times, not a dot product, but a scalar product with the duration of time. Product by a scalar factor. Sorry, the scalar product is a very confusing phrase. So when you look at change of energy and change of momentum, they are related quantities. So that's how sometimes you can get somewhat, I guess, two situations that look similar but are different enough that when people are not paying attention, I can get them. So I think once it's all spelled out this way, you can see more easily. So given the same amount of force, if you want the amount of energy change to be the same, then yeah, you would keep the displacement the same. If you want the change of momentum the same, then you would keep the duration of time the same. And as you change other quantities like mass or whatever, or you might be changing what other forces might be present, and keeping one the same, keeping the distance the same doesn't necessarily mean keeping the time interval the same. All that's kind of captured in this graph. And this is one of the things I like about the simulation, which is that sometimes when we hear the word description and just trying to think it through in our head, sometimes we forget these details. Simulation kind of lays it out. So in some sense, it makes things a little bit boring because it takes out all the tricky situations, the things that might surprise some people. So let me do this. I can actually do a kind of purpose-made simulation of Newton's cradle. So, I've tried to do, and I've done Newton's cradle with the algodo, which is a kind of realistic simulation, does all the pendulum thing and all that. That has its own value. The one kind of slight issue I have with the algodo simulation in that context is sometimes it does weird things. It glitches out for no reason. This simulation is far less likely to glitch out. So I can set it up and I have some reasonable degree of confidence that it won't do weird things. It'll just do the things I want it to do. So, all right, I need to set it up with the right velocities so that these things don't move around weirdly. So in a Newton's cradle, the setup you have is you have 4 balls, or the version I have, you can have any number of balls, but the version I have is you have 4 balls that are at rest, and I can lift one ball and let it hit the rest of them. So I can have one ball coming with some speed, hit these 4 balls at rest. And I have a little bit of a gap between the balls. I think that's going to be fine. Let me just make sure they all have exactly 0 velocity. If they don't, that could mess things up. Yeah, they all have exactly 0 velocity. All right, let's just run the simulation and see. Yeah, okay. Well, yeah. Let me just let it run and not interrupt it. If I click this, I don't know what it'll do. Will it? Let me not click it just because I don't know if it'll go like initialize everything. Okay, I'm just gonna let it run, let it strike, and once it's done the interesting things, then I'll bring it to a stop. Okay, that's kind of the same as what our original Newton's cradle did. But let me see if I can reset. Yeah, okay. And let it run slower. And we'll go frame by frame so that we can look at the details a little bit better. The kind of the details that might have been missed when you are looking at either the algodo simulation or the real life version of Newton's cradle. So this is going to strike, and as it's striking, let me do just the frame by frame. So frame by frame. So you can see that when this ball 1 strikes ball 2, ball 1 comes to complete stop, and ball 2, if you are able to see this velocity vector, you'll see that it has the exact same velocity ball 1 did. This is kind of the feature that you can derive for elastic collision between 2 objects of the same mass where the target object was at rest. You can go through the method to show that, in the collision, the one that came in will come to a stop. The one that's struck will go out with the same velocity. So it goes. Now 2 is actually moving from here to here. It's a small distance, but it's moving. And like 3 frames. And then hits 3. Now it's a 3 that carries on the motion. 2 is at a stop. So what looks like one interaction in that, real life demonstration, or even in algodo, especially with the balls touching, you can see individual interactions. But in this simulation, you can see that it's 1, 2, 3. It's going to be 4 separate collisions. It's not actually one ball came in, one ball went out. It's one ball came in, made the next ball move. That made the next ball move, then made the next ball move, then made the next ball move. So, all right, so that's one demo. Let's make it more fun. let's see what happens if we have two balls coming in. And can I make it so that I wish? Okay, that's good. That's good. I do want to see the actual velocity values. So that way I can make them the same. So let me make this 0.5. And for 2, I'm going to make that 0.5 as well. So now this is the scenario where two balls come in. So 1 and 2, they're moving at the exactly same velocity, so they won't collide with each other. And then let's see what happens. Yeah, let's first see what happens at normal speed, and then we'll step through one at a time. But kind of the same thing you saw with Newton's cradle happens, or with the other simulation or the real life object. So let's now step it one frame at a time and try to make sure that we understand all the quick little things that apparently happen. Right? It's about to collide. I'm gonna zoom in and look at it from frame by frame perspective. So one frame. Okay, it's going to collide real soon. Okay, I think next frame. Okay, it collides. So 2 and 3 collided. 3 is moving. 2 is at rest. And in the time as the 3 is about to collide with the 4, let's see what happens. 1 collides with the 2, so 1 is at rest. 2 is moving again. 3 collided with 4. 4 is moving. 3 is at rest. But 2 is now moving. It's going to collide into 3 as that happens. This is moving. 5 collided with 4. It's moving. 4 is at rest. Now 3 is going to collide with the 4. And 4 is moving. 5 had nothing else to collide with, so it went. So what looks like one interaction in the Newton's cradle, the real life demo, two balls came in, two balls went out. It's can I count the collisions? 1, 2, 3, 4. Maybe 4 times 2, 8 collisions, that or 7, some large number of collisions. And this actually, in my view, illustrates the power of conservation law approach. So even though this is actually quite complicated series of interaction, when you're analyzing it algebraically, you actually didn't have to take into account all the intermediate collisions. As long as you had the confidence that momentum is conserved and energy is conserved with each interaction, you can just do the analysis from the very beginning to the end. You don't have to go through all the intermediate interactions. All right, let's finish up this simulation with the other, 3 balls. You've seen that before. Oh, and this time we can actually see exactly what happens so that 3 balls can go out. So we'll just start with the slow, and then we'll just look at it frame by frame. So let me stop it here. All right, let's do frame by frame. So 3 collides with the 4. 4 moves. Okay, 3 is at rest. In the next amount of time, 4 collides with 5. 5 is moving. 2 collided 3. 3 is moving. 1 hasn't collided with anything yet. Okay. Now in the next time, 1 collides with 2. 2 is moving. 3 collides with 4. 4 is moving. 3 is at rest. 4 collide. Wait, did it? Yeah, 4. No, 4 didn't collide. No, 5 did a collision a while back. It just didn't have anything to collide with now. So 5 just keeps on moving. Okay, in the next frame of time, 2 collides with 3. It's now moving. 4 and 5 didn't have anything to collide with, so they keep moving. And now that 3 is moving, it doesn't have anything to collide with, so it'll just continue to move. So, 3 came in, 3 went out, and there's a more complicated set of interactions that leads to that happening. And let's just end with, for completeness sake, let's do the remaining 2 that you've seen the demo of, with both the real life demo of Newton's cradle, and I'll go do simulation. So we have this. I'll run the next one in real time. Normal time. Yeah. So here with all those collisions, 1 ends up at rest, and the rest are able to just move on. And the case where 5 balls came in, and 5 balls will go out, And in some sense, this is, oh, well, I guess that's all. Well, it's the boring case where, nothing is happening. Now, you can use conservation law strategy when nothing is happening, because when nothing happens, the quantities that you are interested in, they're even more likely to be conserved. So this is one kind of reproducing some of the things you've seen. 2D is actually the fun one. It can demonstrate some of the, well, it can demonstrate what I was showing in lecture with the collisions in 2D. So for that to work, the way you should set it up is one of the balls at rest, and the other ball, let's say, coming, and head-on collision is actually not going to be all that interesting. You want a little bit of an angle, and I think you want to trace out the path. Then you can see after the collision that these two paths are perpendicular to each other. So one of the properties of elastic collisions with two objects of equal mass, so elastic, equal mass, and one of the target at rest. That'll lead to the feature that you are seeing here. The path of the two balls are at 90 degrees. And if you play billiards, you might have been taught that at some point as a way to angle your shots correctly and all that stuff. And this that particular factoid happens to be true for many different collision parameters. So now when it's like a head-on collision, it's mathematically true in a vacuous sense, in the sense that the dot product between the final velocity and the dot product between the final velocity and this velocity is zero, because one of the vectors is zero. That's in the vacuous sense in which that's true. That only happens for head-on collision. If you set it up for any other parameter where it's a little bit off of head-on collision, then this initial velocity won't go to zero, but it's still perpendicular, so that their dot product will be zero. And it remains true for really glancing collisions, where very little of the velocity transfers to the target object. They are still at 90 degrees. If I can make it even more glancing. Oh, yeah. And here it's still true, because this velocity is zero. The product between this and the other velocity is also zero. The mathematical factor doesn't change just because nothing happened. Are they close enough? A little bit more. All right. Now that should be close enough. Yeah. I wish I could make it more glancing. So between those collision parameters, how much this is deflected changes. What remains same is the relative direction between this vector and this vector. That's 90 degrees. And there are many other things you can do with this simulation. I guess I'll leave that for you to play with. That's really the one advantage of simulation, that you don't have to listen to someone else talking only. You can just play with it yourself, and it doesn't have the same kind of difficulty there might be with a physical setup where you need the right equipment and all that. With all this, all you need is a computer or even a tablet or even a phone, because it's an HTML5 simulation.